Okay, so hello everyone, and welcome to our seminar this Friday. Today it's a talk about a tool and a tutorial, in fact, on that tool by Arend Rensink, and we just established that the tool is about 20 years old now, and I'm pretty sure, I don't know if I had known about it really from the very beginning, but certainly for the last 15 years I've been aware of it, and I've myself been a user of it for quite some time. It's one of my favorite tools because it's all self-contained and it supports practically everything that I can think of as important concepts. So along with a number of interesting analysis techniques and so on. So yeah, so looking forward to how this is developing. Please, Arend, take it away.
Thank you, Heiko. Also nice to be here and to be able to present this to some people who hopefully not all of whom are already as familiar with the tool as Heiko is. I'm right now sharing just the page of this seminar, which tells you that you can download the tool and also the rule systems that I'm using. And the idea being that you could play along with what I'm doing, but I don't know how feasible it is in practice. But you can look this up. Don't have to continue sharing it. Let me rather start with the actual presentation. So it's I have some slides, but most of it will be actually a tool demo. So what I want to achieve with this seminar, from my point of view, is well, to acquaint you with the tool, tell you that it exists, that it's still alive. There are some recent developments, but much of what I'm showing has been there for a while now. Not all of it for 20 years, but for a while for sure. And I hope to make you enthusiastic, that you realize, yeah, this is something that this could offer me something when I want to actually try out some of my ideas. This can help me. So get more users, but also get more uses, because I'd like to see what else the tool can be used for that possibly I'm not aware of right now, and also quite willing to extend the tool for uses that aren't yet in view. So in the hammer nail analogy, I have this hammer which is already quite versatile, but I would actually like to see how much more versatile it could get, and then find suitable nails for it to hammer in. And of course, eventually, this could serve as a source of inspiration for my own research, further tool extensions, case studies, or even collaborations. That's always a good thing. Right. That said, yeah, get feedback. I'd like this to be a interactive meeting insofar that's possible for an online seminar. So that means that I welcome questions either by audio or by chat. I'll try to keep the chat in view, although, yeah, I'm also using that part of the screen, so maybe I see it all the time.
I can have a look at, I can monitor the chat and let you know if anything comes up there. Yeah, that's all right.
Yes, let's do it that way. By the way, I have this Zoom ribbon in view on the top, which I think might interfere with my controls for the tool. Well, let's try and see if that
happens. Think you can move it somewhere else. You can grab it and move it around. Yeah.
I can grab it. Yes, I can grab it. Okay, let's see. You don't see what I'm doing. I'm now grabbing and playing around with this toolbar. Okay, let's go. Yeah, go on. Yeah, this is already on the website, so let me skip that. This is a list of the features that, when I was preparing this, I thought, okay, this is what I'd like to show. Now it's a long list, and it's probably too long for 1 hour. So I'm pretty much expecting that I won't get through this. Certainly not if you, as I hope, ask questions. So let's see if that happens, and if that happens and there's interest in hearing more, then you could have a follow-up or something like that. Okay, but I'm not going to take you through this now. We'll get there when we get there. It's just to tell you that it's going to be quite a number of things that I want to say. But let's get to it straight away. The basic functionality of the tool is how you can model stuff. So I'm now jumping into the actual tool and showing you a screenshot of the tool, and I hope this is visible enough for you. So what you see here is the traditional wolf, goat, and cabbage puzzle, which I'm going to assume that you actually know. So it's more like how this is now modeled in this tool than about what particular application it is. The way I've modeled this, and I know there are many ways to do it, but my main purpose is to show off the capabilities of this tool. The way I've modeled this is to have two nodes standing for a right and left bank, one boat that's moored to one of those banks, and three items that are on a bank. And you see here likes edges to tell you that one of these items or animals or living beings likes the other to the degree where they will actually eat it when the boat is not around. Two rules here, one of which tells you that the boat crosses without anything in it. And okay, now I have to say something about the way this has been encoded. What you see here is two banks with an arrow between them saying they are not the same bank, because here matching of rules is typically by default it's not injective. If you want it to be injective, you have to do something, and this is the way to say that the two bank nodes of this rule should be matched injectively. Then there's a boat node as well, and now we have two colored edges which tell you that things are deleted respectively created. So that the blue and dashed edge tells you that a node is deleted. The green and somewhat fatter edge tells you that an edge is being created. The same goes for nodes. They are not deleted or created in this particular rule, but the color coding is the same. Now, if you think of this rule as in the more traditional span format, then it would be the blue and black part is part of your left-hand side. The black part on its own is your interface graph, and the black and green part is part of your right-hand side. Plus, of course, this injectivity constraints, which is not really part of the traditional rule. Okay, so this is the case where the boat goes over without taking any items with it. This is an alternative rule where there's an item which is either the wolf, the goat, or the cabbage, which goes with the boat to the other bank. You see it's that node is untyped. I'm now in a setting where there is no typing around. I'll say something more about that in a minute. But otherwise, there's not much surprise here. The eat rule is a bit different, or it shows you a bit more stuff in the sense that now you see a node being deleted, and also you see a red arrow, and that's a negative application condition. So that's not part of your left-hand side. Actually, it's an extra negative application condition. Again, I'm assuming that you are acquainted with this notion, but even if not, it's easy enough. This rule is only applicable if the boat is not moored on the bank where these two items are, one of which likes the other, and the thing that is liked then disappears because it gets eaten. So this is the eat rule. Okay, let's see what else is to be said about this. Yes, I was telling you this is the untyped setting. There are ways to make this typed, but let me first show what you can actually do with this. So starting in the start graph, you can actually, on the left-hand side, you see that these rules are applicable in a number of ways. You can actually click on that application and see where it is applicable and actually execute that at that spot, and then you get to the next state. So the boat is now on the next bank. You see, by the way, that the location of the node doesn't change. It's just the edge that changes. The layout is static here, and this is all very much abstract syntax rather than concrete syntax. There's no real animation in the view. I'm going to back to the initial state. because there's now you see that the cross-empty application has been explored, and you see that it goes to a next state called S1, but there's still 3 cross-loaded applications, one of which is crossing with the wolf, crossing with the goat, and crossing with the cabbage. And well, if you know the puzzle or think about it for a second, you realize that the right thing to do is to cross with the goat here, but they are all possible, and you can apply them. If you cross with the wolf, double click, then the boat and the wolf are on the other side. And now you see that in this next state, the eat rule is enabled, because the boat is not on the bank where the goat and the cabbage are, and the goat likes the cabbage, so the goat eats the cabbage if you give it the chance. And gone is the cabbage, and the puzzle is now unsolvable. So that is basic functionality. There's also a condition here which tells you when you have solved the puzzle. This is just a pattern, it's not a rule. It doesn't change the graph, and therefore it's called a condition here rather than a transformer, which are the things that actually change the graph. And this will match, obviously, when you solve the puzzle. Now, besides manually clicking through the rules and trying it out and seeing if you modeled things correctly, the very important part of the functionality of this tool is to do this automatically. So there's a tab LTS over here, which if you click it, shows you the things that I've just explored manually. So I started over here, which was the initial state. Then I tried out crossing empty, which means that I'm over here, and that was this state. So you can play it back, but even more importantly, you can just restart and do it all automatically. This gives you the entire state space of this puzzle, which is too large to really investigate visually. But you can do stuff with it to investigate it automatically, and you can here still visually identify the state where the finish rule is enabled, and you can then also say, let's highlight a path from the initial state to that finish. Let's see, where is that? I'm looking now for show. Yes, show trace from start state. This is the solution to your puzzle. So that's a very straightforward way to do something with a rule system. As long as it's as simple as this, you can do all this visually and manually. And now, actually, if you go back to the start state, the rule that will get you to the next state is start, so you can really play it through and see what the correct solution is, like this. Or look at the states and do the same thing. So that's sort of the basic functionality. This can all be typed instead of untyped. That is, there is a type view as well, which is currently disabled. This is the type graph of that whole puzzle, and you see, well, everything that you saw is seen now in the shape of a type graph. If I enable this, like this, then first of all, some errors crop up, because now the tool complains that there are untyped nodes in my rules, which is true. Of course, I showed you them. The type graph has been set up in such a way that you can type this, because, for instance, this item in the cross-loaded rule, yeah, it could be the wolf, the goat, or the cabbage. But in my type graph, there is a super type of those, so I can say this is an item. I said typing type item, the rule the node gets typed and the error goes away. In the each rule, the same thing happens with 2 rules actually. This one should be typed item. This one should, so this has, if you click on it, you see how the deletion is actually specified underwater. It's a prefix del : meaning this is a node that is to be deleted, but it's also typed, which is on a different line, saying it's a typed node called item. Now I have the same system again, but it's typed, which is advantageous because There's some slight performance gains, but especially as typical for anything, when you type it, the documentation gets better, and you might actually catch some errors that you made, just typos. I want to point out that not only is there subtyping that's supported, but also this item is an abstract type, so they cannot have actual nodes with type item. They must always be of a super type. This likes edge, which exists on the item level, is an abstract edge. So you have to respecify it on the concrete level. Wolves can like goats, and goats can like cabbages. But if you would try to specify a wolf that likes a cabbage, and I can show you that it actually complains if you do that. If I add to this start graph a wolf likes a cabbage, then it will complain saying a wolf node has an abstract likes edge, which is forbidden. So in that sense, well, but nothing new here. It's just I'm telling you that Groove supports this. In that sense, typing can simply help you get your system right. Okay, let's see. Is there more I wanted to say about this? Yes. Currently, if you explore this, and I did this so quickly that I'm sure you couldn't see it, but if you explore this, then if you do get to a state where something could eat another thing, you could also still harmlessly go back, for instance, from this state by crossing empty, you can back to the initial state. Of course, in the actual puzzle, you want to avoid getting here in the first place, and if you get here, you want to make sure the puzzle becomes unsolvable. You can do that by giving the eat rule a higher priority. So rules have priorities, and in particular, it's easy to say raise priority of this rule. Now I have a priority 1 transformer, which is the eat rule, and priority 0 transformers, which are the others. What happens here is that the tool always first tries to apply rules with a higher priority only if they are not applicable. In the first place, the left-hand side doesn't match, then lower priority rules become applicable. The condition is exempted from this, so conditions have no priority, they are always applicable. Otherwise, you might not detect that you're in a state where a condition is satisfied. So if I now explore, then in a rule where I can eat, I cannot do anything else. So means that the transition system gets smaller, and you can concentrate on that behavior that you actually want to have. Okay. So again, I'm showing you features of the tool on a particular application. The application itself is maybe appealing, but of course not that interesting in itself. It's a well-known puzzle, and also a feature that I want to show on the basis of this particular example is the isomorphism checking. That's actually one of the features that is very hard to get if you don't take a graphical view of things. So it's a kind of symmetry that is obvious when you have graphs. It's not of course algorithmically easy to check, but it's an obvious notion if you have graphs. And let me show what it does in this particular example. So if I take out the left and right labels from the bank, then you see there's potential symmetry here, because now it doesn't actually matter on which bank the things are. If all of them would be on the right-hand side, then it's symmetrical. Of course, my finish condition will now never be satisfied. In that sense, this is not the perfect example to show isomorphism checking, but I just wanted to show you that it exists and that it works. Because why can't it be satisfied? Well, the finish condition says all of them have to be on the right bank, and I just removed the right flag from the bank, so this can no longer be true ever. But the point is that if you now go to the transition system and explore it, then it's quite a bit smaller than before, just because all the isomorphic states got collapsed. So if during the exploration you meet a state, always it's checked, did I see this state before up to isomorphism? If yes, then it's not a new state. Instead, you go back to the thing you found before. So in this particular example, it does already also give you advantages because of a smaller state space. If you have an example with larger degrees of symmetry, then this can really mean a lot. I see a question by Detlef. What algorithm do I use for isomorphism checking? This is something that I did publish about some time ago. The idea is it's a kind of a partition refinement algorithm, and that, well, the idea is that you look at the direct context of two nodes to see if they might be isomorphic, and you essentially increase that context until you stabilize. And then this gives you a sort of a hash code for your node. It's in a certain, say, neighborhood with a certain shape, and other nodes that are in the same neighborhood with that certain shape there might be an automorphism from one to the other. And to see if they're redirected. So this is an approximation. It's essentially an overall approximation of your isomorphism check. If two graphs have the same hash code in this sense, they might be isomorphic. Then you still have to check if they're actually isomorphic by just, well, trying to find an isomorphism, trying to find the actual isomorphism. That is potentially still quite expensive. However, the graphs that I've tried this on, we did several case studies to see if this really brings you an advantage. The graphs that we tried it on are not in the specific classes where it gets so expensive that you still spend all your time isomorphism checking. So there are plenty of examples where this pays off to such a degree that the time taken to do the isomorphism check is outweighed by the time saved because you have a smaller state space. Okay, right. So that is, say, the basic functionality. Let's see if I showed you everything I wanted to show. Let's show you typing. I didn't actually talk about type and flag labels, but I did talk about type versus type rule system. So what are the type and flag labels here? These left and right things were special edges that are always self edges and are recognizable because they're preceded by the word flag. So that type it again, then it's this is the left bank, this is the right bank, and that's done by this special. It's essentially a node label, but actually implemented as a binary edge, which, however, is always a self edge. The same holds for these types. They look like types. They are bold-faced, but underwater they're actually self edges with a specific label, which in this case is a type label. So that's the thing about type and flag labels. I showed you, I didn't show you the multiplicities. I actually want to show you the multiplicities as well. You might have seen it when I showed you the type graph. Well, this just tells you the boat is moored on exactly one bank, and the bank has either 0 or 1 boats. Obvious, this is what you want. However, the advantage of putting that in your type graph is that if you make a mistake, suppose that, for instance, in this rule you said, oh, okay, I forgot to delete the edge. So now I cross, but I'm also staying at the same bank. This actually violates that particular multiplicity. If you try to apply the rule, you see it becomes pink rather than light blue. You get an error message saying that the multiplicity is violated. And in your transition system, this state is marked as an error. So this actually is another typing feature, which in this case cannot be statically checked, right? Multiplicities cannot be statically checked, but they are checked dynamically. So it's a bit beyond the notion of type graph as typically encoded in our community. You say a type graph is just something that I have a morphism to, right? My typing is a morphism to a type graph, and I can statically ensure that rule application never violates the typing discipline because I can ensure that the result of the transformation is still well typed. That can't be extended to multiplicities, but there's this dynamic feature of checking that that helps you there. Okay, that was that issue, and the rest I did talk about. So let's go on. I did, of course, already show you something about exploration, but there's more to be said here. I'm going to demonstrate that on another version of the same rule system, wolf, goat, cabbage version 2. The only difference being that rather than having an eat rule, I turned the possibility that something gets eaten in a condition instead. So the condition mealtime says, well, it says the same. This is actually the left-hand side plus negative application condition of the eat rule that we had in the previous version. But now it actually doesn't eat. It only marks that something can be eaten. So being a condition, and this is the feature that I actually want to show, being a condition, you can mark this condition as being a forbidden condition. So rules have properties, in particular, conditions have properties, and you see here the action role is one of these four possibilities. It was either transformer, which is if you change the rule, if you change the graph, or it's a forbidden property, it's an invariant property, or it's an ordinary condition. In this case, this would be a forbidden property. So I'm saying it's a forbidden property, save the rule. You see on the left-hand side, this changes into what's called a safety constraint. Now, what about that? The safety constraint also, just like typing errors, show up as errors in your state space. So now you have already a better way of seeing that your rule system can lead you into erroneous states. Not only that, but you could now also say, I actually, these things that violate my condition, I want them not to be part of my state space in the first place. So now that I marked this as a forbidden property, I can say, and now what I'm doing is going to so-called grammar properties. The grammar properties can tune a lot of things, and now in this particular case, I'm going to the action policy. The action policy tells you that for this invariant, no, for this forbidden property, mealtime, I want this to be absent. This is not right. Let me see, check the syntax that I need. It's not absent, it's remove. So it's mealtime is remove. I think I need a colon apparently. That's better. It says I need a equals. Okay, there's a bug, a small documentation bug here. Okay, mealtime is removed. Now I change this action policy. If I now explore, then those states that violate my mealtime forbidden property are simply not there in the state space at all. So I just left them out. And this, of course, reduces in this particular puzzle the behavior to that part that is without errors. And now it's really is only the part of the puzzle that contains the solution. And you see there are two solutions. Obviously, first you do the goat, and then you go back with the empty boat, and then either the wolf or the cabbage is next. So that's how this branches over here. But later on, you reach the same state. So this is a way to use properties to actually reduce your state space and make it more manageable. Besides that way of doing things, I'm going back now and going to say I don't want this action policy. I want the full state space, because there's something else I want to show you as well. And so far, what I've done when I automatically explored is to push this button over here. And if you hover, and you get a tooltip saying this means I do a BFS /final/infinite exploration. What does that mean? Well, actually, you can tune the way the state space gets explored quite a bit. the standard setting is you do breadth first exploration. The acceptor is final states. Well, what is an acceptor? What are final states? An acceptor is when you say I have reached a desirable state, and a final state is one that doesn't have any outgoing transitions. There were no final states in this rule system because you could always go back and forth with the boat. So you haven't seen that, but that's the default setting. And infinite, the / infinite, just meant I go on forever and not stop. I don't stop exploring ever. But you can say that I explore until I find a state that that is accepted. So if I find a final state, for instance, that doesn't make a difference here because there are no final states, but it does make a difference as soon as I say my final state is not, no, my acceptor doesn't look at final states. Instead, my acceptor looks at invariants. I don't know why these are called invariants, but my acceptor looks at states where the finish rule is applied. So now, if I explore, it will stop exploring as soon as I have found a state where the finish rule is applied. Which it does, and it calls it a result state. Over here, you see it has stopped exploring. How do you see it has stopped exploring? For instance, it doesn't give you the cross transition back to the original state, and it doesn't go on either. So this does what I promised it would do. Having seen that, you can also do things like depth first exploration rather than breadth first exploration, which I think is going to get you typically gets you to the solutions faster. I don't know if this was faster. It certainly avoids some of the states that we saw before. There's linear exploration, which might not find the solution at all. It doesn't in this particular case because it goes to it applies the wrong rule and gets to an error state, and then because it's linear, it doesn't backtrack, so it stays there. There's the random linear, which well, might not do anything either, but it might do different things, as you see. It gets to different places. Well, not always. This is not a good example of random behavior. It does the same thing all the time. I don't know, maybe it's the same seed for the random behavior. I don't actually know. Well, the idea is that this is random. So what I'm showing you is just that in this automatic exploration, you can tune it. And this, depending on what you actually want to achieve, might be quite beneficial. For instance, if you're bug hunting and you want to find the shortest path to a state that violates some property, you can use breadth first exploration because that will give you the shortest path, and then stop at the first state that violates that property, and thus you might avoid actually well, very long lasting or even non-terminating explorations. Okay, I'm talking and talking. There are no more questions, and I've switched my view of your faces off, so I can't see if you are looking puzzled. So without any questions, I will just continue with what I have had prepared.
Sorry, there was a question. Detlef asked, what does Prolog do?
What does Prolog do? Ah, you're looking at the other. Yes, there is this one, I think. That's the Prolog window. No, that's the type window. Now I'm. How do we even see that? Because it's not.
I think there's a window for Prolog, is there?
There's a Prolog window. You can actually query the graph. You can query the transition system using Prolog queries over here. This is a feature that was built in, and I personally haven't used for a long time. So this is not on the list of things that I had planned to demo, and I'm happy to do so, but I would have to prepare it because I'm not that familiar with this function.
Yeah, don't worry. But okay, but it's a good question because I had that question as well, I think at some point, and I didn't really go into it. But right, so the idea is that you take the transition system as a relational structure and write Prolog queries
Yes.
about
Yeah.
it? Or
Yeah, I don't know if you
the
see
level of the transition system or on the graphs as well?
So the product queries don't care what you're querying. You see, there's a lot of built-in predicates here,
I see.
which do lots of different things, and some of them are about states and transitions, and some of them are about the internal structure of a graph.
Okay. Oh, so that's more powerful than the temporal logic.
It is not strictly more powerful, but it does allow you to do things that temporal logic doesn't allow you to do, and vice versa.
Okay.
Well, maybe you can actually also define your own product predicates. So maybe
if you can define recursive predicates, it's probably more powerful than.
Then maybe it is actually more.
I don't know.
Yes. There is a large caveat here, because this was developed so long ago and not really actively maintained. I wouldn't put my hand in the fire for all these predicates still doing exactly what they were designed to do.
Okay.
But I'm quite happy to revive this if there's interest.
Okay. Well, thanks.
Yeah, the fact that you're asking about advanced features might mean that I'm going too slow, but that's hard for me to judge right now. So I'm just going to continue with the things I did prepare. There's one thing that might have struck you if you thought about it. If you do this exploration, and let's go back to the standard. You don't actually see within the transition system. You don't see much about what's actually going on. In particular, if you have a cross-loaded rule, you just notice on the transition system that something has been loaded, but you don't know what. And in many cases, it is actually useful to expose that part of the match of the rule application on the transition system. And this you can do using parameters. So the cross-loaded rule here can be parameterized in the following way. You can actually say the item that I am transferring becomes a parameter of the rule. This is done by saying it's a parameter, and that in turn is done by saying par : 0, par for parameter, and 0 is the parameter number. You can have multiple parameters. They start counting at 0. Now the rule, I mean, you can see that there's a parameter because there is on the top right and left hand corner, there's a number 0. And you can see it in your transitions, in your matches on the left hand side, because this now has a N3, N4, and N5. Okay, what are N3, N4, and N5? Those are actually node identities. Those are the node identities of my wolf, goat, and cabbage. I don't know which is which, by the way. You can't see that from node identity. It actually exposes the internal structure of the graph, and because formally the nodes are just they have some arbitrary number. That is the number you see. So if you now explore, you do see on each of the cross-loaded rules what was loaded. You don't know what is what, but you can see when you go on that, for instance, here apparently I took the thing back, that here I took over, and that's very likely to be the cabbage. Sorry, the goat. Of course, you can check that. And for being the goat, is N4 the goat? Yes, N4 is the goat. So you get a bit more information on your transition system through these parameters. Later on, if we get there, I'll show you how else you can use the parameters. And in some cases, you can use data values there, which do give you better information than just node identities. Right. Let me get back to my slide and see if I told you everything that I wanted to tell you. The tool features based on the example. I showed you exploration strategies, which are strictly explored part of the state space. I showed you conditions. I didn't show you invariants, but they are the complement of forbidden conditions. Expression policies, which was the case where I said, okay, now I don't want the erroneous states to be part of my state space, so I restrict the actual state space through setting that in the grammar properties, and I did show rule parameters. It might strike you as though what I wrote under expression strategies and what I wrote under expression policies is quite similar. In both cases, you restrict the state space, but there is a conceptual difference. The expressions policy just really takes a state out of the state space. It's no longer part of the state space that you're considering. Using expression strategies, you look only at part of the state space, but the things that you don't look at are still conceptually there. So you just traverse the state space in a different way. So with the policies, you make it really smaller. With the strategies, you traverse it in a more clever way. For instance, model checking, which is at the end of this talk, is also an expression strategy. Just try to be clever in where you go. You can have heuristic expression strategies. Just make clever choices about which part you explore. Doesn't mean that the things you don't explore aren't there. You're just not looking at them. Okay, this may be obvious, but I wanted to stress it. Okay, having shown you quite a bit of the basic functionality now, I just also want to briefly spend some time, well, explicitly presenting the underlying philosophy. The idea here has been from the start to provide a way to rapidly model your problem domain. So it's about rapid prototyping. Get going very quickly. You just install this tool. You start clicking. You have your first graph. You start clicking. You have your first rule, and you can try it out, and it gets you going very quickly. Then the second thing is that when doing this and going a bit further than your very first clicks, you want to be able to model things easily. And modeling things easily for me means offering powerful ways to model those. Obtain compact models in terms of number of rules. Also stay close to the problem domain. So don't really, the idea here is that if conceptually something is a node, you can make it a node. If it's, you don't have to somehow encode that node in some other properties. And in this way, it's definitely different from, say, the more traditional model checkers, which don't have this underlying graph formalism, and you always have to think about how to encode your graph structure. And the third thing is really state space exploration. Both the manual state space exploration, which allows you to check the correctness of your modeling setup and allows you to do small examples to see if everything's right, and then go to the automatic state space exploration, which really is meant to analyze the overall behavior. And there's multiple ways to do it. I already shown you some ways, and there's more. For instance, the model checking. Now, there are essentially three ways in which you can apply graph transformation, I believe. And I think Heiko and Gabi also wrote about this in the software engineering book. You can use a graph transformation system to define a graph language or parse it if you apply the rules in the reverse order. So that's the traditional view of a graph transformation system plus a start graph being a graph grammar. Or you can use a graph transformation system to define a relation over graphs. This is, for instance, what happens in model transformation. That means you set up a bunch of rules. They are in principle confluent, if not even deterministic, but confluent meaning the order in which you apply the rules doesn't matter. You always eventually get to a point where this is your target graph, that is maybe your transformed model, and it doesn't matter in which order you apply the rules, it's always the same thing. Or you can define a transition system or a transformation system to define the behavior of your domain, behavior of a given system. For instance, that was, of course, what I did in the wolf, goat, and cabbage system. I defined the behavior of that system given the rules that I encoded it with. And then you can, well, find solutions or whatever else you want to do. That's different yet, because now you don't have confluence typically. Your rules can be non-deterministic. Now, I think it's probably clear that this is really Groove's main strength. This is what it was designed for initially. That's what I had in mind. It can do the other things as well, but not necessarily the best tool to do those other things. Yeah, so that's something that you could keep in mind. Now, in the actual implementation, there have been further choices. As you noticed, this is all implemented in Java. That has great benefits, but also disadvantages. Benefit being cross-platform, not always, because, for instance, on the Mac, you shouldn't use the built-in Java, as Nick has already discovered once more. You should install the Oracle or the Open JDK. But I mean, overall, I don't regret this choice. But yeah, memory performance of Java is notoriously bad. Time performance is not that bad, but there are certain languages in which you can do this better. Another design choice was to make it a standalone tool. I've not integrated in any IDE. Both benefits and disadvantages. Benefits being you're your own boss. You're not dependent on whatever goes on with that IDE. Take Eclipse. I think every version has a different plugin mechanism, so you have to maintain that all the time. But now you have to do your own GUI, and a lot of stuff you have to do yourself, which is certainly not ideal, and does give rise to bugs, unexpected ones from time to time. The standalone tool can also be invoked command line. Another advantage, by the way, I think it's an advantage that this gets you going more quickly. And if you're in Eclipse and try to do something, there's so many buttons, so many possibilities that this can become overwhelming quite quickly. Graph visualization is not very good because it's on the level of abstract syntax. You can't have nice visualizations of your graphs. There's a bit more than I showed so far. You can actually color nodes, and you can have so-called edge nodes, which means that it's essentially a node that stands for an edge, and it can be displayed a bit better so that it looks like an edge a bit more. But I'm not going to show that. It's all abstract syntax, and yeah, that's what you're stuck with. And it's strongly centered on the notion of a graph transformation system, here defined as a fixed set of rules. So you can't dynamically create rules. You can't change rules in the course of the transformation. It has a start graph. Well, you can have a set of potential start graphs. You can create new start graphs, but it has also always it takes a start graph and runs from there. It does have an optional type graph control program, and actually there's Prolog. There's also Groovy. You can do some stuff in Groovy. I'm not going to demo that either. So that's the way things have been set up, and those are choices that are now not really easy to get away from anymore. So that's what we're stuck with, what I'm stuck with. And yes, this is another one, and that's not, that's something to be aware of. The underlying graph model here is simple graphs and not multi-sorted graphs. So edges don't have identity here, which means you can't have two edges with the same label between the same two nodes. And that in turn means that I like to present things as though they adhere to the categorical view, but it doesn't. It does not actually faithfully implement SPO. If you try to create an edge that is already there, it will just not create the edge. It will, reuse the one that was already there. That does not always bother you in the sort of models that I've actually looked at myself. It was never a problem, but it is something that you need to be aware of. This is something that potentially could be changed, but this is not high on my list of priorities. So it could be you could extend this to multi-sorted graphs. Right, I see some questions here. I think SPO, so to Barbara, SPO in the category of simple graphs. Okay, let me try to get this right. I think the things it creates are not pushouts. No, and that is because in the category of simple graphs, I think I can't recall this. I would have to think about it. Then when I'm talking, it's hard to think. But I'm pretty sure it is not SPO in the category of simple graphs. Yes, that's certainly true, Nick. If you restrict your setup so that you never delete or create an edge without also deleting or creating one of its incident nodes, then it becomes then essentially you're encoding multi-sorted graphs in your simple graphs, and then it certainly adheres to the categorical setting. And Detlef was saying something about the algebras, and that is actually the next thing on my list. So that's where we're going now. And I see that it is 10 to 4, which means that we have 10 minutes, which I think means that I can just cover the algebra part, and then time will be up. So let's do that quickly and then see how we continue. Right. No, okay. The next thing was extended rule matching feature. I'm going to skip that because I do think that attributes are more interesting. Okay, attributed graphs. I have an example here where I want to show how that works. It's a very simple game. This is your start graph. It has a pawn, locations. There's one location that's a finish location, and there's a die. And here you see the first occurrence of attributes. This die has 6 edges, all called eyes, but they are points to different values. Those are integer values in one of the sorts that is provided by default by Groove. The fact that there are multiple edges to the same to different values of that data type will already tell you that the underlying formalism here says the graph gets virtually extended with all possible values of the basic sorts that are supported, and those are integers, real values, strings, and booleans. And my attributes are actually edges to those values. And here, this die node has edges to 6 different values, and this is the way that it's shown. If you then do something, so what is this game about? It's an incredibly simple game. You first throw a die, and then and so this says throw a die. What does that mean to throw a die? It creates a node called throw with an attribute called value, and the value is initialized to one of the 6 possible values of the eyes edge of the die. So this says d.eyes. What is d.eyes? Well, that's the eyes edge outgoing from the D node, and the D node is this one over here. You see here underscore D colon die. This means this is the node that has locally the name D. So d.I is essentially a field of this node D, and the field is an outgoing edge that goes to an integer value. This thing down there is a negative application condition. Just you don't create a throw if a throw has already been created. So this is one way in which you can set a field just by giving it value. If in this case it's a new node. Then there's a rule called move, and this does 2 things. On the throw node, which must be there, you change the value edge. You change it from its current value to its current value -1. So this is essentially deletion of an edge and creation of an edge, hence the plus minus there. It also says that you should only do this when the value is larger than 0. So that's a condition under which the rule is applicable. So you see here there's subtraction of integers, and you see there a comparison of integers, which gives you a boolean, and in this case that boolean just has to be true in order for the rule to be applicable. Initially, the rule is obviously not applicable because there's not even a throw node. But once I do a throw, so let's do a throw. The throw is 4. Now my move rule becomes applicable because there's a throw node, and if I apply it, then the throw node gets decreased to 3. And also the pawn moves, because that was the other part of the rule. the pawn moves just to the next location. So it's a very stupid game. We just throw and then move the pawn as often as the throw indicates. So value 2, value 1, I win, but I also still have a throw. So I can go on with the throw. Now the value is 0, which means the rule is no longer applicable. The third rule says, if I have a throw with value 0, I delete the node. So altogether, this tells you that, well, you throw a die, you move as many places as the die shows that you can move, and then you're done. As I said, well, the game is simple, but the point here is to really illustrate the attributes. So this is a very, yeah, this should hopefully give you an idea of what is possible. There's a bit more that this doesn't show, which I can add by just modifying this rule. Because there's also a thing that's called a local variable. I can say there's a local variable which is an int, which is initialized at d.is. So, well, that's not very useful. And so far, I'm also going to give this a name. So that this is the throw. So now it's a local variable called throw, initialized at d.is. And rather than using d.is here, I can use throw here. Okay. Does exactly the same thing, but with one intermediate step where this throw first gets assigned to a local variable and then to the value of the created throw node. The advantage being that I can now also make this a parameter, as I did before with the object that I was moving across in the wolf, goat, and cabbage example. So again, this is par 0. Now, the number that is thrown is actually exposed on the throw rule. So it becomes a bit better to see what's actually happening, because every time you throw, you actually see how much you've thrown. Detlef, to what degree does this answer your question? That's maybe not the best way to ask that. Let me just continue, because there's something more to be said here. Detlef. Isn't there tool support for SMT checking, certified by module theory checking? That would be nice to have, but it's not there. It's not there in Groove. So this is all very concrete. You're saying exactly what goes on. There's something that goes a little bit in that direction, which I did want to show, because this is using. You might ask yourself, to what degree is this theoretically valid? What is actually the algebra that I'm using? And the answer to that is I'm using Java. So the algebra that I'm using is not actually, they are not actually integers, they are Java ints, which are 4-byte approximations of integers. But here, Groove does offer a bit of an extended feature, because you can say there's different algebra families that I can use. So far, I've been using the Java algebra family, which is the default one. But there's also the so-called point algebra family, where every type has only a single element, a single value. There's a big algebra value where, instead of the Java ints and reals, using the implementations that offer arbitrary precision, namely big integer and big decimal. And there's a term algebra representation. So that's a bit also from a theoretical point of view to satisfy my own curiosity. But if you set the point algebra value, then the behavior becomes quite a bit different, quite a bit smaller, because now what happens is that when you throw, there's only one value to throw, which is always 0. And then, of course, well, how is it possible that you can even move, although the value is 0? Well, if you look at the move rule, what's happening here is that the value gets decreased by 1, but the only value is 0. All values get mapped to 0, so it stays 0 if you decrease it by 1. Also, it gets compared to 0, but the comparison always gives you the same value, which is actually should be the value false. So the rule should not be applicable. I forget what the default the one value of the Boolean type is in the point algebra. Okay, the point being that the purpose of having the point algebra is that you can use it to analyze the behavior of your attributed system, which quickly can get infinite in a much more reduced fashion. So the idea is that this makes it smaller and so helps you in actually analyzing your system. I also want to show the term algebra is a bit of a theoretical play, but it's interesting I think it's interesting to see, because now if you throw, it still doesn't really do anything. Okay, this example is not a good one to demo the term algebra on. Okay, sorry about that. I should have prepared this better. I'm going to stop here because that takes us too far if I try to explain what just happened. So, about algebras, the tool features I just demoed or talked about and partially demoed are the fact that Groove does support these 4 basic data types. I showed you int, I showed you test, which yields a Boolean. There is also reals and strings there. Computations that are supported are, I think, all of the standard arithmetic operators. I'm actually right now in consultation with Raiko, who wants some user-defined operators. So that's going to be in the next extension. You can actually define your own operators in some Java class that has to be loaded together with Groove, and then you can do much more advanced stuff. Maybe even user-defined data types, but that's the next step. First, user-defined operations on the existing data types, then maybe user-defined data types. In order to manipulate attributes, Groove offers these fields and variables together with node names. There are these algebra families. I don't think that I was very convincing in demoing them, but they exist. And this is something I didn't show. Let me do that briefly, and then I want to see if this is a right place to stop. So, algebra family, back to the default one. The throw rule here had the creation of a throw node under the condition that it doesn't already exist. That is something you meet quite often. You create something if it doesn't already exist. I mean, this actually also harks back a little bit to this SPO discussion. If you only create something under the condition that it doesn't already exist, then you will never get parallel edges. So if that holds for all your cases, then you are essentially you have a rule system where the SPO semantics is faithfully adhered, just because you will never get outside the situation where your simple graphs do the job. But so because it is a commonly appearing pattern, there is a way to combine that. Instead of saying it's a new node, you can say it's a conditionally new node, which then creates a throw in case it's not already there. However, not quite. Not quite, I say, and then it works. Okay, that did the trick. So the conditional, that's what I wanted to show you, the conditional new creation. That's the last thing on this slide. Okay, people. It's 4 o'clock. I went through a lot of stuff. I can imagine that you're saturated. I feel some of that saturation myself at this point. I'm not at the end of the things that I had on my list. Just to go back to what I had on my list. There was this list, and I barely got halfway. No. Sorry. This was the list. So, Nico, Raiko, what do you think? I actually feel that this is not really the best idea to continue at all costs.
I mean, not now, but I think I'm quite interested in those advanced features, and if we want to schedule another session on this in a month or so, I think that would make a lot of sense. I mean, not now is, I mean, we start talking about nested rules now, then we need another 15 minutes even to explain why they are needed, I guess. Yeah, but I would like to have just another session on this. I wouldn't mind.
Yeah, me too. And also if you could have, I mean, for these features that you're showing, I mean, it would be very nice. You had like a lot of examples in this folder you shared with us. Now that we saw maybe the basic functionality, and I mean, I just put all in, I mean, how to run it on Mac, which was apparently the one odd case. One can do this, and next time we might actually play along a bit, maybe, I don't know, because I would be quite interested to play with the advanced features myself, if possible.
The one doesn't rule out the other.
Exactly.
Yeah, you have the examples which obviously show you a rule system that contains those advanced features. There were things I wanted to say about them, which could still be useful even so. So I did see this coming, so I already asked Nick in advance, would it be possible to schedule a follow-up? And yes, it is possible in a month or so. And I'd be happy to do that because, yeah, I don't mind talking about my own stuff. So I'm quite, but there should be enough interest from your side. So that's more the question.
Yeah. I mean, it's also good to have this, as you said. I mean, it's recorded, it's available for posterity on YouTube. So it's good to have a somewhat comprehensive tutorial, I think, available. So it's even apart from the people who are here, I think that may be interesting. I had a question about the term algebra, just to understand what it does. So is this really just the algebra which doesn't have any identities in it, essentially, so that you have
yes.
Okay.
Yeah, and I must say that I was a bit surprised that it didn't do anything, but I think it's due to the value larger than 0 test. Because what it does is to compute the value of that test and then compare it to true. And the value of that test is, in this case, the term value larger than 0, which of course is not the same as true. So the test straight from the bat. Yeah, I think that's what's happening here. So in that sense, the example is just a bad one to show the utility of the term algebra. But okay, I actually brought this up partially in response to Detlef's question, and that is a thing that I myself have been thinking about and never got around to doing anything with, because definitely the whole thing has been set up to make the algebra potentially flexible. And you could, and it doesn't even have to be an algebra. It could actually be a relational structure where, and so this has the potential of also defining domains that are abstractions. Like, I mean, take as a very basic example the abstraction of the integer saying plus, 0, and minus, right? With operators on it that are not operators, because if you add a plus and a minus, it might be plus, 0, or minus. But if you multiply a plus and a minus, you know it's minus, stuff like that. So And and there are of course much more advanced abstractions of data values. Those there is definitely the potential to build those into Groove and run your rule systems on a data domain that then isn't infinite. And you might even think about predicate abstraction, and then you do get in the direction of SMT solving, as Detlef suggested. So, Detlef, saying you have a problem with Zoom, so maybe it's not something we can discuss right now, but okay.
As you just said, to ask if anybody else who wants to ask a question can unmute themselves, because maybe we have a technical problem.
Well, Heiko can unmute.
Yeah, but I'm probably co-host.
Barbara,
I can unmute, I think. So okay, you can hear me now, right?
Yeah, works for me.
Yeah.
Okay, good.
So I'm not sure what the issue is.
It must be a local thing that
should we maybe quickly, Heiko, should we close a YouTube stream maybe, because then we can make a quick plan amongst everybody who's still here, so that it doesn't get too late, and then everyone who still wants to discuss could stay offline. Well, first of all, thanks a lot, Detlef. Detlef for letting us know of the technical problem. But I meant, of course, Arend for the very nice talk, very interesting. Just wanted to mention that next week we already have the speaker for next week here in the group, Carlos, who will tell us in 2 weeks about hierarchy algebras. And then hopefully, I'll send out, of course, an invitation if Arend tells us a date that works for him. I think it would be very good to have a second round. It's more in-depth experiment.
Let's agree to do that, and then nested rules will be there, control will be there, both of which are big. Well, there's
and testing with nested conditions, maybe.
I think
model checking also. That was only in brackets on your slides, but
well, it's in brackets because
that's because
supposed not to be in time, maybe.
Sorry, Paolo, I didn't get that.
The model checking was in brackets probably because you thought that you wouldn't have reached that point.
Exactly, and I didn't prepare it because I was pretty sure I wouldn't get there. But for next time, I will prepare it, and then the brackets will be gone.
Right.
Yeah, let's do that. So I could.
So let me quickly just stop the YouTube live stream and say thanks to the YouTube audience.
Yes.